or the collection of personal comfort data for the city of Brisbane and the project that we are working on. So in terms of the agenda for today, I will start with a short bio, so some information about myself and also the whole research team behind me. Then afterwards, I will just, make sure that we're all on the same page, and we'll repeat some information about conventional comfort modeling. And before I dive into the actual presentation, then I would like you guys to get involved. So I'm using Menti to get some feedback from your side, from the industry. And yeah, after that, I'll move over to the actual presentation with an introduction, some information about my project, the field study that we conducted, and there in more specific way about the method, results, and also the potential the results showed. And then I will close everything with a short outlook to the future and a conclusion. And hopefully after the presentation, you guys have lots of questions that you want to ask me about our research. So first of all, about myself. So as you can probably hear from my accent, I'm not Australian. I'm originally from Germany, and I started my education in the field as a civil and environmental engineer. And during the studies in that bachelor degree, I became interested in buildings and energy efficiency in buildings. And I decided to become a mechanical engineer in my hometown of Münster in Germany, in Western Germany. But when I started my job, I realized pretty quickly that the influence of energy efficiency of buildings as a mechanical engineer can be quite limited. Usually you get involved quite late in the project, and sometimes you only can fix some of the can fix the buildings, but you can't actually change the design and the passive performance of the building. This is why I decided to continue my education and do a master's in energy efficient building design or climate design at Lund University in Sweden. And when I finished that degree, I was happy to get a role as a building science engineer in a big architectural company in Germany. So worked as a consultant with architects and got that kind of influence that I was looking for in the first place. But then after just like 1.5 years working as a building science engineer, I got the offer to go to Australia and start a PhD here at QUT. And this is why me and my girlfriend, we moved to Australia 3 years ago. And what I also liked about my PhD that I'm able to teach students in bachelor's and master's degrees, and I'm teaching in basic building science, passive design, and also building performance simulation. But yeah, my PhD wouldn't be anything without the great team behind me. So I have a perfect combination of good supervisors and also co-authors in my publications, which are from Australia, Sweden, and also UC Berkeley in the US. And this is a great multidisciplinary team behind me, and I'm really grateful that I have the help and support along the way. So everything that I'm talking about today wouldn't be possible without the team behind me. Yeah, and as I said, before I start the actual presentation, I just wanted to make sure that we're all on the same page. So when you guys, as I think most of you are like sustainability consultants in the industry, I think when you think about thermal comfort, you probably think about the predicted mean vote model, which is used in air-conditioned buildings, or the adaptive model, which is mostly used in naturally ventilated buildings. And I just wanted to give you a quick reminder. So the PMV model is basically a model that includes 6 variables, 4 environmental and 2 personal variables. These are then the input of an equation that delivers the predicted mean vote of comfort between -3 and +3. And what we usually want to achieve is a PMV between -1 and +1, or in some stricter cases, even -0.5 to +0.5. And the PMV model is based on experiments that have been conducted in a climate chamber. So there was a cohort of people who were sitting in that chamber while the environmental conditions and the clothing and metabolic activity was changing. And all these findings were then put together into a model. The adaptive model on the other side came out 20 years ago, so later than the PMV model. And that's actually, this model actually uses data collected in real buildings all around the world, and uses a simplified approach where we only look into the indoor operative temperature and the mean monthly outdoor temperature, or the running mean.
Sorry, Toby, sorry to interrupt. I'm just making sure that you are going through your slides, because I can only see the first slide. I think we all can just see the first slide.
Okay, that's weird. Let me just do it again. I think it's the sharing the wrong screen. Let me just do it again.
Yeah, no worries.
This one. Sorry about that. Okay, do you see the slide now?
Yes.
Yeah. Okay. So yeah, I just go back then. So about myself, I think I mentioned everything. So visualization, then the team behind me. So now you can actually see the people that are in the team. So as I said, great people behind me. And now just a short repetition. So we have the predicted mean mode on the left side and the adaptive model on the right-hand side. And continuing with my explanation about the adaptive model, that's actually a pretty straightforward way, because we only have two input variables, the indoor operative temperature and the mean monthly outdoor temperature, or running mean. And then we relate these two variables to each other. And usually the goal is to get in that comfort band to create indoor climate conditions which are comfortable. So these are the two conventional models. And in today's presentation, I will mainly talk about the predicted mean vote model, because the data that we collected is from air-conditioned buildings. But as I said, before I start with the actual presentation, I think that first of all that you guys should have your say. So I created a short question on Menti. So you can just scan the QR code here, or just go to menti.com and use this code to access the question. And then feel free to just answer the question in whatever way you like, and then we can briefly address your answers before I go on. So let me just make sure that you guys see the answers. All right.
I think if you keep the code and the QR as well next to it, it'll be good. So people can, okay, great. Menti code.
Yes, that's interesting. That's basically what I expected. So never write, cold buildings. These are the answers that we get from most consultants. Also, comfort definitely critical for occupant satisfaction. Unfortunately, when we talk about thermal comfort, it's often discomfort that people experience. Chills from sitting under a diffuser. These are the answers that we get most of the time. So this is actually a very good picture of the general situation. Ideal temperature and humidity is actually what we want, but unfortunately we don't get it most of the time. So maybe we just leave it here, and I will continue with the presentation, and then we can go on later, or can come back to these answers later. Also make sure that you don't go to the next question just yet, because the next question is supposed to be answered after you've heard all the information that I'm sharing. All right, let me go back to the actual presentation now. So just to make sure, do you guys see my presentation now? I hope so.
Yes. Okay,
perfect. So let me just start with the actual presentation and a short introduction. And I'm an engineer, so I like numbers. So I thought, why not start with some basic numbers? And the first number that I want to talk about is 3 times. And what this number represents is that the cooling demand is expected to triple by 2050. That's the consequence of climate change, because we have warmer outer conditions, but also it's a consequence of the increasing building stock all around the world. But what it definitely says is there's a significant challenge. And in that context, there's something that we call a vicious cycle, because climate change itself and the more extreme conditions, they put a lot more pressure onto buildings, which then have to use more energy to keep the indoor climate comfortable. But this again, because we have to use more energy, is actually exacerbating climate change because of the greenhouse gas emissions. So this is why we call it a vicious cycle. But what I think, and what other researchers agree, is in the middle of this vicious cycle actually is thermal comfort, because thermal comfort is the main reason why we actually design buildings. We want to create a space for people to be productive and feel comfortable to live in. And it's also the intersection of all these points. And this is why I decided to focus my research on thermal comfort. Let's move on to the next number. So next number is 34 or 34%. I don't know if you know, but 34% is the prediction accuracy of the PMV comfort model. That means that only in 1/3 of the cases, the PMV model actually gets the thermal sensation of people in a building right, which I think is very, very low. So just as some context. Then the next number, 50 or 50 years, and this might or might not be connected to the previous number. That's the time since the introduction of the PMV model. So the PMV model was introduced at the beginning of the 1970s. So that has been 50 years now. And if you just think about what happened in terms of technological advancements throughout the years. So shortly after the introduction of the PMV model, we got access to personal computers. A couple of years later, around the millennium, we all of us got access to the internet and things like Google. We are now using smart mobile phones on a daily basis. And since a couple of years, we are also starting to use self-driving cars. So there has been a lot of like technological advancements, especially in the last 20 years. But in terms of comfort and comfort research, we are still using models that are 50 years old. I don't want to say that comfort or that the PMV model is a bad model, or because in the end it put thermal comfort into focus, and it was the first time that we actually started to think about thermal comfort at all. But on the other hand, we just have to acknowledge that the model was developed a long time ago, and by that time, the model was limited to the technological progress back then. But over the last 50 years, so many things have happened, and this should give us a lot of potential to upgrade the models that we are using at the moment. One way to upgrade the models is the use of something that came up in the last, I would say, maybe 5 to 10 years, and that's the use of artificial intelligence, or things like machine learning and data science. And people and researchers have started to use artificial intelligence and machine learning for thermal comfort prediction, and it showed very promising results. But the problem about these technologies is that we need a lot of data for them, for an accurate prediction. The problem here is that the conventional comfort standards, they require us to use equipment that's very, very expensive, and that brings us to the next number, $3,800. That's the average cost for one set of monitoring equipment or comfort monitoring equipment when we want to meet the requirements of norm or the common comfort standards, which I think is very, very expensive. And what that problem also creates is that researchers and all the people who want to use that comfort monitoring equipment, they can't afford many sets of it, and that also limits limits the variety of data, because usually you can only install one set of monitoring equipment in the middle of the room. And what happens is that you might pick up the mean indoor climate conditions, but you don't monitor the conditions that people are actually experiencing in their microclimates they're sitting in. Like, for example, getting the draft from a diffuser or something like this. I think that was also mentioned in the question before. So this is another strong barrier or significant limitation. To get the data, you have to spend a lot of money. And just as a comparison, so for that project, we developed a low-cost monitoring device for personal comfort data. And for this amount of money that we're seeing here, so my last number, we can, instead of getting one monitoring device, we get 40 of them. So that's, if you get 40 devices instead of one, you can go much closer to participants. You can collect much more data. Everything is much more pervasive. So just as a short summary of the introduction, first of all, we have rapidly increasing demand for cooling. Only 1/3 of comfort predictions are actually accurate. The models that one model that we are using is based on prediction methods from the 1970s. And the equipment that we have to use to get comfort data is very, very expensive, which limits the potential for things like artificial intelligence and machine learning. So these are the problems that that we discovered. So what we tried is to develop a PhD project based on these problems. So the PhD project tries to answer the question how climate change impacts personal indoor thermal comfort in Australian buildings. And we have 3 distinct stages. So in the first stage, we developed the monitoring device, calibrated and tested it. In the second stage, we took the device into real buildings, performed a field study. And now at the moment, we're starting to analyze the data and use machine learning to propose some advanced data-driven thermal comfort models. And then the end goal is to include everything into a simulation concept that also allows us to bring in future weather data of high quality to make a prediction about thermal comfort in the future and under the more extreme conditions of climate change. The whole project is under the main line of learn buildings from buildings. So we try to use data that we got from post-occupancy evaluations in existing buildings to inform the design of new buildings. And we actually, we try to consider 4 keywords so that everything is personalized, that it's localized, integrated, and also one key feature or characteristic of this project is that we want to make everything open source. So we want to share everything with the general research community so that our other researchers and interested parties can benefit directly from what we've found. And before I dive into the field study and the results or the findings that we made, this is just a short overview of the project. So we started with the monitoring device in the first stage, then we conducted the field study, and now we're using our collected data and the data that's already existing to perform a data analysis and work on the data-driven thermal comfort modeling approach. And as I said, everything is open source, so we will have a GitHub page with all the information that you need to build the climate boxes. Also, we are planning to release a comfort data analysis toolkit called Comfort Dat, and also a simulation-based individual model package called Comfort Sim, but more about that in the later slides of this presentation. So as I said, next step, the actual field study and what we found. Before I start talking about the field study, what I want to highlight here is that this presentation is based on the paper that I presented at the Australasia Building Performance Simulation Conference a couple of weeks ago. And all the findings that are included here are preliminary. So because we are still in the reviewing process of the actual paper with the full data analysis, I only can share the preliminary results. but they already show a pretty strong picture of the whole context. In terms of our field study, so the concept that we applied was to use the small boxes that we created, so the monitoring devices, and position them very close to participants, so on their desk. And then we simultaneously send very short questionnaires, most of the time three questionnaires per day, to these participants, sometimes on their mobile phone, sometimes to their laptops or desktop PCs, and then they answered these questionnaires, and afterwards we combined both these different data sets and got the data samples that we needed for our analysis. And the main goal of that field study was to make everything user convenient, because if you work in or collect data in office buildings, people have to work and you can't interfere with their daily working routine too much. So this was the main goal. And also we wanted to have a device which is calibrated and which is open source, so that other people can use our findings for their own research. So this is just a short sneak peek of our device called the Climate Box. Again, we're still in a reviewing process for that publication, so I can't share too much information. But what I can say is that the three main goals, we call them AAA, so accessible for everyone, affordable for everyone, and also accurate. And what this device does is that it only uses off-the-shelf sensors that are available to everyone, puts them together in one device, and it measures all the main comfort variables that you need to collect in a building to, for example, calculate the PMV value. And as I said previously, we will share everything from building instructions over the printed circuit board files to program code, 3D printing files for the housing that you can see on the left-hand side, and also the calibration data. So other people can benefit from our experience and use it as a basis for their own research. And now I want to talk about the results in more detail. I'll try to keep it informal, and I won't go into too much detail, and I try to keep it light. So first of all, what we looked into was how did the participants engage, and how was the experience for them? Because as I said, one of the main goals was to make it as user convenient as possible. And what we found is that we actually achieved that goal, because the response time per questionnaire was relatively low. It was only 45 seconds as the mean value, which is under our goal of 2 minutes. And what we also found is that we could prevent user fatigue, and most of the participants sent or submitted around 10 questionnaires or samples per week, which is a great number. And back at that time, so it's preliminary, as I said, we had 475 data samples, gathered from 48 participants. And I will talk about the final numbers later. But before I actually talk about the results, what I want you guys to keep in mind that is at that stage of the research, we had some kind of an uneven distribution. So if you look into the age group and also the gender distribution, it's kind of imbalanced. So when I talk about the results, please try to keep that in mind when you make your own interpretation. All right, results. First of all, let's just start with the descriptive results about thermal comfort in general. So usually the main thing that you're asking is, how do you feel right now? So the questionnaire followed the right here, right now approach. And when you look at the graphs here, so thermal acceptability, thermal sensation, and also thermal preference, what you can see is that most people in that questionnaire actually indicated that they perceive the conditions as comfortable, which is actually a good result. So this actually shows that the building that we are working in, they function quite well. So that was the first result. But if you look a little bit deeper, discomfort or cold or discomfort on the cold side. And that's is very easy to pick up when you look at the histogram in the center. So on the left-hand side of the neutral vote, you have many more votes on here, especially for slightly cool and cool. And if you think about the climate of Brisbane, which is actually pretty warm all year round, this is kind of the results that you don't want to see, because it means that in a warm climate, people feel too cold, and that's usually connected to a use of energy for cooling that can be avoided. And these findings, they're kind of accompanied by the results that we got for the thermal preference, because although most of the people indicated that they don't want any change, there are more people who want warmer conditions than there are people who want cooler conditions. This is, fits into the picture pretty much. Then the next step was that we looked into the comparison between the data that we collected and the conventional PMV model. And a variable that many other researchers use, and also we did use, is PMV discrepancy, which is nothing else than the difference between the PMV model prediction and the actual thermal sensation vote by occupants. And usually, what you see on the left-hand side is a heat map, so you can see the direct comparison of the PMV prediction and the actual thermal sensation. And what you want to get is very high numbers on the main diagonal, because that actually shows that the PMV prediction, they're the same than the actual thermal sensation votes. But I think from looking at these graphs, you can pick up pretty quickly that the predictive mean vote model didn't perform that well in this field study. So in comparison to the number that I presented earlier, we found that in our field study, the PMV model was right in 38% of the cases, which is slightly more, but still not really convincing. And what we also can say, just by looking into the fields above the main diagonals on the upper right corner, and also in the histogram in the bottom right corner here, is that we have many more votes on the right hand side, which means that the PMV TSV discrepancy is positive, and that basically means that the PMV overestimates. So to make it a little bit easier, so at, for example, a temperature of 23 degree, the PMV model might say comfortable, whereas the actual thermal sensation of people in that building is much lower than the actual prediction of the PMV model. So this is why we say the PMV model overestimates comfort. But this is only the PMV comparison. The next step that you can do in the analysis is to use also contextual factors. So in this study, a pretty important contextual factor was the location. So our data field study took place in Brisbane, and what we did is that we compared the collected data to already existing data sets for other locations in Australia. And in order to make it easier to compare the locations and the different data sets, we limited the data sets to air-conditioned office buildings only, because this is the type of building that we collected data in, and also narrowed everything down to a temperature range of 23 to 24 degrees. And what these box plots show here, if you look at the different locations, is that this temperature range is perceived differently in all the cities that we looked into. And even more interesting, at least we think that it's interesting, is that they seem to be in order of the climate. So what I mean with that is that these temperatures, so 23 to 24 in Brisbane, they're perceived mainly as slightly cool, whereas in warmer climates like Townsville and Darwin, they are already perceived sometimes as cold or cool, so cooler than in Brisbane. On the other hand, climates which are a bit colder than Brisbane, at least for some parts of the year, in Sydney, Melbourne, and Kalgoorlie, this temperature range is mostly perceived as neutral. So it's perfectly comfortable. What this shows is that there's definitely, this is an indication that there's an influence of the location and outdoor climate on thermal comfort in air-conditioned buildings. And that's something that the PMV model doesn't incorporate just yet. So the question here is, with all the data that we have all around the world, do we need custom comfort models? So do we need comfort models for specific regions, for specific locations around the globe, just to make the prediction more accurate and to not continuing to waste this energy for cooling or making our buildings too cool? And this is how, where I want to proceed with the outlook. So the questions that I raised on the last slide was, do we need to customize our comfort model? And what we did then is to use the prototype of our comfort simulation package and thermally simulated, a validated Brisbane simulation model for four different cooling set points, so from 22 degrees to 25 degrees. And based on these simulations, we got an indoor climate data set for the occupied hours in an office building. And then we used first the PMV model as it is, and then a custom model that's based on real data that we collected and that's existing in the ASHRAE comfort database. And we compared the prediction of these two models. And what you can see is that for the occupied hours at a cooling set point of 22 degrees, the PMV would predict 92% of comfort throughout the year, whereas the machine learning model, which is based on actual data from buildings, says that only 32% of the year would be comfortable, with the main reason being people feel too cold at 22 degrees. And if you look at the other side, at the more extreme of using a cooling set point of 25 degrees, the PMV here would say that it's only 43% comfortable. The main reason here, people perceive the conditions as too cold. But again, the machine learning model, which is based on real data, predicts a totally different results. And what this could mean for the energy efficiency of a building is, you can see that in the last row here. So if we increase the cooling set point, just as an example, from 22 or 23 degrees to 25 or 24, there's potential for massive energy savings. And what this also shows is that the PMV model is not only not accurate, but also that it can have a very, very bad impact on the energy use in buildings. And what that causes is that we have occupants who are uncomfortable, and we have lots of energy use that we can actually avoid by making our building a bit warmer. So maybe we should think about customizing comfort models or having models which are more regional and dynamic. So one good reason why we are able to do that now is that with the accumulation of the ASHRAE comfort database, we have data from many, many countries, many climate zones around the world. So what you can see here is a visualization of the world map. And then on a logarithmic scale, colored in purple, are the countries where we got the data from. So if the color is a bit darker, that means that we have more data. So what you can see here is that we have enough data from North America, from South America, Australia, Europe, Asia. So there's lots of data that we can already use. And if we keep in mind that now with the trend towards low cost monitoring equipment, we can even gather more data in different locations around the world. This can actually pretty promising direction for future comfort research. And in the end, data is key. So if we are able to collect more data, then we will also be able to increase the prediction accuracy of our models. So I just want to conclude with 5 points, and these might be your main takeaways from today's session. So first of all, I want to highlight the potential of low-cost monitoring devices. So the device that we have built was around $75. So that's much less than the actual cost that the common standards require. The next point is only 1/3 of comfort or PMV predictions are actually accurate, and that has the consequence that the temperature ranges the PMV model is proposing, they're just too narrow, and we have to use a lot of energy to achieve these temperature ranges. So that means that there's a significant potential for energy savings, and with the data that we have, and now that it's easier to get more data and more variety and quantity, let's use new advanced technologies to improve the prediction accuracy of our models. And again, just keep in mind, these findings are preliminary, and in the next couple of weeks, we will hopefully publish the full papers where you can read more about the research and more detailed investigation of our results. And then in terms of our future work, so I just wanted to close everything and come back to the numbers that I originally presented. So first of all, what not only our findings, but also findings by other researchers have shown is that when we use machine learning based comfort models, or models which are driven by data and more advanced technology, we can actually double the prediction accuracy of a comfort model. And I don't think that I need to tell you what that would mean for the energy efficiency in buildings. So this should be the goal for the next couple of years. And also, if we collect more data, what that would allow us is to reduce the cooling demand in the future, maybe through customized or dynamic and local comfort modeling. Also, another finding, as I just told you, we can reduce the cost of a standard set of monitoring equipment from $3,800 to around $80, or even less. Depends where the technology goes. So maybe we might need to accept a little less accuracy for more quantity and variety in data. And also, this is something that I just mentioned at the beginning. Again, I don't want to say that the PMV model is bad. It has done a lot for the whole field of research, and it's a very good foundation. But why shouldn't we use the technological advancements in the last years to upgrade the models that we are using? And this is just a short outlook about what we are trying to achieve in the next couple of months and what we are hoping to publish. So we started with the climate box, so the building occupant explorer. So that worked pretty well. And now in the next step, we want to maybe get even more data, but first of all, analyze the data that we have. So at the moment, we have just over 800 data samples, and these are from 91 different participants. And then soon we hope to publish a data analysis toolkit that allows to compare collected comfort data with data that's already available, look into distribution, correlation of different variables, maybe even clustering algorithms, so you can get more personalized or cohort comfort modeling approaches, so that in the end we have a different, or let's say a new way of predicting comfort that can supplement the conventional ways that we're still using. And then in the last step, also very important, is that we at some point have to integrate these models into a simulation workflow. That's what we want to do with our Comfort Sim package. So what we try to achieve with this is that we get a way to include comfort in early design stages, to get early feedback on thermal comfort in buildings, to improve the passive performance of a building and put the passive performance of a building into focus, because that's also very important for resilience. just think about power outages in the future to reduce the over-reliance on mechanical conditioning of buildings. And strongly connected to that is the potential of PCS, so personal comfort systems. We also try to integrate into our package or component. And last but not least, what we also want to do is to integrate or include high quality future weather data. So for Queensland, for example, there's a big data set or big database of RCMs, the regional climate model data that we can use, and this will hopefully allow us to make more accurate predictions. So that's about the outlook. Before I go on now, I would like to get you guys involved again to conclude everything, and I'd like to know if there's anything about thermal comfort that you think needs further research, improvements, or upgrades, or something that you're interested in. So again, you can just scan the QR code or use the code at the bottom of the page, and I will just move to the other screen or to this slide to see what you're thinking. So voting is closed, so I open the voting now. Should work, I hope. So see what you guys think. And again, I keep it open so we can come back. We can come back to this question. Okay, relative humidity I hope it means relative humidity considerations. Yeah, that's definitely something, and that's also where research is heading, because the adaptive comfort model, for example, doesn't directly include relative humidity. So that's a very interesting way to look into. Yeah, as I said, I might leave that open so you guys can still share your ideas or your questions. And I will just want to conclude my presentation with the last slide. So if you guys want to get in contact, again, you can just send me an email, shoot me a message, or scan the QR code, which will lead you to my LinkedIn profile. And also I want to acknowledge the funding that was provided by the Building 4.0 CSC and the Ost Industry CRC program that helped us with our research. All right, thank you very much. I will stop sharing my screen and give over to Manasa, I think, again.
Yeah, thanks so much, Toby. That was amazing, a great presentation. We have a lot of questions in our Q&A, so I'm hoping you are able to answer that. I'll just go through them as many as I can. Then, so Prachi asks, how much did it cost to make the instrument that you were talking about in the early part of your presentation?
Yes, so at the moment we have built 20 devices, and if you narrow it down, they would be at $75 each. But it's something that if you order like all the components in bulk, you would be able to reduce it even more. And also we decided to get all our components from Australia. You can also order them from overseas, and that will even drive the price further down. So at the moment we are calculating with $75 per device, Australian dollars.
That's great. Another question was, how do you know that resonance's perception of the scales in thermal sensation both were aligned? Like, does cold, warm, etc. mean the same as temperature or sensation for all of them?
Yeah, so there's actually, I can't remember the paper now, but there has been research has been a team of researchers, psychologists who looked into this. So this whole comfort scale is actually a very, very well established scale that has been used and tested in a lot of studies. I don't know if I'm answering the question at the moment. Let me just reread it in the chat to see.
Yeah,
so
no worries.
maybe, yeah.
We can come back to that, and maybe you can link us to that particular document you're talking about, so we can look at that. So we can get back to that. PC Thomas asks, was there any study on the impact of RH, which is probably relative humidity, because a higher dry bulb with a high relative humidity could change the thermal sensation to sticky and uncomfortable?
Yeah, one of the findings so far was that it's actually pretty hard to say something about it, because the buildings that we investigated, they had very narrow ranges of relative humidity, of air temperature, so all these values were constant and in the desired range most of the time. So this is why we couldn't say too much about the correlation of the relative humidity as a single factor. That's something that we are looking into at the moment. So in the end, that's a problem about doing comfort research in air conditioned buildings, that you only have let's say a very limited or small range, because the conditions in most buildings are the same all of the time, right? So this is why we can't say anything particular about the relative humidity itself.
Yeah, makes sense. And it's Brisbane, they probably have RH control usually for the offices. Right. And we've got a question from Pete Zachariah. So he talks about how PMV or like challenging cooling set points in PMV already tells us the limits of comfort. And PMV already tells us that we can relax operative temperatures to about 26.5 degrees and still maintain a PMV of less than 0.5. But does this study by any chance show how much further we can push that range?
No, so we haven't. Let me just reread the question. Saying this not so. Could you maybe just can Pete maybe elaborate the question a little bit more? Like I don't get what he means. Do you maybe just turn on your mic?
Pete, if you're online, you could just turn on your microphone and ask that question.
Sorry for that.
No, that's all right. Hi, Toby. Hi. So my question's about challenging cooling set points, because you mentioned that relaxing it would lead to increased energy savings. But it's not really the comfort model that's stopping us from relaxing set points. The comfort model, like typically commercial offices are conditioned to 24 degrees, which tends to be on the negative side of PMV if you account for the correct clothing. So noting that there's room in the PMV model to relax cooling set points, does your model potentially say that we can relax them further beyond what PMV is telling us because it overestimates?
Yeah, I think the PMV, operative temperature is not the only input. You still have it's very critical. The two main inputs here are clothing and metabolic activity. So these are very personal variables. So if you want to achieve a PMV between 0.5 with 26.5 operative temperature, that would mean that you assume very light clothing, I guess. And the question here is if that actually is a good representation of the actual conditions in buildings. So what we found is that in lots of the office buildings that we investigated, people were actually wearing suits or long clothing, like this very formal degree of clothing. And if you if you do that, and you obviously can't bring up the operative temperatures to 26 degrees. Maybe I still didn't get your question right. But what you were saying is that so what do you think is the problem with cooling set points? Why can't you do this?
You did answer my question well, so thanks for that. But the issue is, I guess, historically, it's just leasing requirements. So very conservative tenant leasing representatives say you need to condition to 22.5 plus or minus 1.5 degrees.
Yeah, and even like in building codes or certification systems, you sometimes see that. I think it's I think it's quite remarkable. But as I said, what we found is that clothing is a big thing. So it's also about behavior and giving people more freedom to change their clothing, adjust their clothing. And what we found, and that's one of the main findings, and that's similar to other findings, is that it very much depends on the outdoor conditions. So we did the study in the summer and in the winter. In the winter, the PMV model was actually quite okay, was much better performing than in the summer. But the more extreme the outdoor weather is, the less accurate the PMV model performed, at least on our data set. So that's another impact factor.
Yeah, I guess that Pete's always been for lowering the standards of office wear. So I guess we'll be coming into office in our sandals and shorts soon. But you back that up. So that's great. We've got a few more questions coming in, but I am very mindful of the time. I guess, Toby, I know you can see the chat. Do you want to pick on one particular last question and then answer the rest maybe on our LinkedIn page, or would you like me to just pick it?
I mean, I can. Let me just screen. So Ruth is asking, what's the impact of moving between the home environment and the office? So that's, I would probably say that the main problem here is psychologically, because if you work in your home environment, you can control everything by yourself. You can wear what you want. You can turn on the air conditioning or leave it off. You can open the windows. You can do all of that. But then if I just think about the room where I am in at the moment, you can't turn on or off the air conditioning. You can't open the windows. So this is already a pretty, let's say, pretty significant factor that will make you feel uncomfortable much easier. So this is, and especially if you're moving day by day, we haven't looked into that because we don't know when people were at home or when they went to the office. That would actually be a study by itself to see how people perceive comfort at home and in the office. But usually the psychological factor and the impact of control is very important here.
Yeah, 100%. That's, I guess, how a lot of residential buildings we keep in mind when we design them. Just as to close off, I think Noni also mentions it'll be great to see how this sort of research will be applied to different types of building types as well. So it's like not just offices, but how it reacts in like aged care buildings and health buildings.
Yeah, definitely. So there will be, I guess there will be big differences. One thing is that it's pretty hard to get in buildings like hospitals, for example. And on the other hand, what we first of all focused on is like office buildings, because this is where people need to be productive. This is where they are throughout the day when we have very high temperatures outside. So this is why we picked office buildings first. But then obviously the next step will be other building types. Schools, for example, is another very interesting area. And we are hoping that we can look into that as well in the future.
Yeah, that's amazing. I guess that's all we have time for. So thank you so much, Toby, for just saying yes and giving your time and sharing this amazing presentation. It's very, very concise, very graphical, very easy to understand. So thank you so much again. I guess just to close off this, we just want to remind everyone that the upcoming event for the next IBPSA event is on Thursday, the 6th of October. As we said in the beginning, it's a hybrid event. It'll be both in person and online. So it'll be a great time to network, and networking starts at 4 p.m. and the presentation starts at 4:15. And this is again presented by Noni, who's the principal consultant at Carney Quest and a PhD candidate at UNSW, sharing her research on energy modeling practices, processes to minimize the energy performance gap. Again, thanks so much, Toby, for today's presentation. And thank you, everyone, for dialing in and being an amazing audience and asking all the right questions. I guess I'll stop it here. Have a great afternoon and see you next time. Bye.